This example is to illustrate how we can use potential energy to look at the work done by gravity and to show that the choice of reference level doesn't make a difference. It can make your life easier or harder. So to do this, what we need to do is have a little picture where we have an object traversing different levels. So let's say what we have is something like a little roller coaster or just a track. Something like this. And let's label a couple of heights. Oh, I don't know. Let's call that 10 meters. We shall make this height 5 meters and this one 2 meters. And let's just say we have this ball, and for easy sake, mass of 1 kilogram. And what it is going to do, we'll say it is going to go from point A over here and end up at point B over there. And the goal is, let's find the work done by gravity using potential energies, or potential energy due to gravity. So all of our examples will use this formula. The work done by gravity is PE gravity initial minus PE gravity final. So all of the problems, everything we will work out, will use this formula. So the goal is going to be to use different reference levels to calculate potential energies and show that it doesn't matter where we chose the reference, the work done by gravity is the same. However, choosing a good reference level can make things easy. So what we'll do is we'll label things. So this is going to be example part 1. So if we are going to calculate potential energies due to gravity, you must define a reference. All the reference means is, at this level, it's really about height levels. This is what I am determining the potential energy due to gravity to be 0. I can call it whatever I want. Literally, you get to choose. This is where I am determining potential energy to be 0. So for problem 1, here's what we're going to do. We're going to make, right here, for 1, PE due to gravity 0 at the ground. So this is how you label a reference. You just write PEG equals 0 at the point you label as the reference. So let's calculate the work done by that little ball going from A to B, using this as a reference. Work due to gravity. PE gravity initial minus PE gravity final. So usually the first thing you do is look for zeros. The only time PE is 0 is when the height above the reference is 0. So if you look at A and B, neither term is 0 because the height is always above the reference. So what do we have? This is mgy initial minus mgy final. I'm not going to factor out an mg just so we can do some calculations. 1 kilogram, 9.80 meters per second squared. Y initial? Well, that's 10 meters above the reference, minus 1 kilogram, 9.80 meters per second squared, 2 meters above the reference. So what do we have? This is 98 joules minus 19.6 joules, which is 78.4 joules. That is the work done by gravity when the object goes from A to B. We want to show that this number is not going to change no matter what the reference is. So here's another reference. In this problem, I didn't care that the ball rolled to the bottom and back up. When we say that we care about choosing a reference, the lowest point we're concerned with, I'm going to now choose my reference at B level, because this is all I really care about. So for number 2, I'm going to choose PE gravity 0 at the level of B. Well, work due to gravity. PE gravity initial minus PE gravity final. So what you always want to do is look at initial and final. So to make things clear, sometimes it's actually good to label I and F. And then you just ask yourself, is there a potential energy initial? Sure. Is there a potential energy final? Well, there is, but it is 0, because when it is at B, the reference was chosen at B. By definition, the reference is where we want the potential to be 0. In other words, it can't fall and do work to B when you are at B. That is another way to think of the reference. So this term is 0. So the work is mgy initial. Well, 1 kilogram, 9.80 meters per second squared. So now y is not 10 meters. The height above the reference is 8 meters. And notice you get 78.4 joules. Now you can choose other points as a reference. You should not, in general, choose points above any other point that you care about, or you will get negative potential energies. You really don't have a negative height, but the best way to think about it is you have a negative height. So let's say what you decided is you wanted to choose the reference at A. Not a good choice, but you can do it if you want. So let's say for 3, we chose this. PE due to gravity is 0. We're going to go through the same thing. PE gravity initial minus PE gravity final. So let's ask yourselves, you still start at A. You're going from A to B. That's not changing anything where you define the reference. Well, if you are at A, can you fall and do work? And the answer is no. No. So at B, you're not at A, so there must be a potential. We still have a minus there. So it's mg y final. Well, let's see what this is going to be. So it's negative 1.00 kilograms, 9.80 meters per second squared. However, y, since y is measured downward, this is going upward. Easiest way to think about it is to call y negative. Theoretically, y isn't negative. The whole potential energy is negative, but it's easier to think about it. Since you have to go up, the height change is from here, all right, from B to A, negative 8 meters, because you're going up, and you still get 78.4 joules. Why? No matter what, gravity does 78.4 joules of work when the ball goes from A to B. Because ultimately, by formula, work is F cos theta delta x. And remember, if you really think about it, what's happening? If you want to do the work done by gravity, the force is mg. It moves a height h, and the angle between mg and the way it moves is 0. Mg points down, and it's moving down, so it's mgh. And if you think about mgh, 1 kilogram, 9.80 meters per second squared, and the height change is 8 meters, which is 78.4 joules. This just shows you get the same answer for the work done by gravity every single time. Notice, the potential energies individually are different. For the first problem, the potential energy at A is 98 joules. For the second problem, the potential energy at A is 78.4 joules. And for the third one, the potential energy at A is 0 joules. All of the individual potential energies are different, but the work done by gravity is the same.